Today we're going to be solving radical equations. In other words, solving an equation where the variable is under a square root. The main idea that we need to know as a tool to solve any of these equations is that the square root function and the square function are inverses, meaning they undo each other. So we're going to use this main idea to solve all of our radical equations. So our first one is the most simple. We have the square root of x is equal to 9. So we can see that the variable that we're looking for, x, is under the square root. So to undo the square root of x, we are going to square both sides. Now we know that squaring and square roots cancel each other out. So the square root of x squared would just be x. And then 9 squared is 81. And we can obviously check our work to see that if I plugged in 81, I get 9. Now as I start to get slightly more complicated, the main idea here is that we need to isolate the square root before we can undo anything. So I can see right here that here's my square root. It's being multiplied by 2, and then we're adding 5 to it at the end. So as the first step of undoing, we're going to subtract 5 from both sides. And we don't want our square root to be multiplied by 2, so we're going to go ahead and divide by 2. So now that the square root is all alone, we can undo the square root by squaring both sides. So the square and the square root cancel each other out, so we're left with the fact that x is equal to 9. And of course, we should check our answer. So we will go ahead and check right over in the margin here. So we think x was equal to 9. So as our check, if I plug that in, will this give me 11? So I know the square root of 9 is 3. So I'm going to change that to be a 3. 2 times 3 is 6. And of course, 6 plus 5 does equal 11. So we have found the right answer. Another type of problem that you might see is when there's square roots on both sides. So if there are square roots on both sides, you just want to keep them separate on both sides and do what we did before. So that we have isolated the square root here. There's nothing before or after it. We've isolated the square root here. So now that they're all by themselves, we're going to go ahead and we're going to square both sides. So the square and the square root undo each other. So we get 3x plus 1 will equal 7x minus 19. And then we have a nice little linear equation that we're going to solve. So I'm going to subtract 3x from both sides. And then I will go ahead and add 19 to both sides, just because I'm trying to isolate the variable. And we don't want x to be multiplied by 4, so we'll divide by 4. So we do get that x is equal to 5. Now, of course, we have to check that. The big idea here is that we have to plug it into both sides of the equation, so we're going to check right over here. So we first are looking for the square root of 3 times 5 plus 1. We're trying to see if that'll give us the same thing as 7 times 5 minus 19, all under the square root. So I'm going to simplify under the square root here. 15 plus 1 is 16. Then here we have 35 minus 19, which is also 16. So yes, we have found the right answer because root 16 is equal to root 16. Now in a problem like this, we can see that there are 2 square roots, just like the last problem, but on this one they're on the same side. So the first thing we always want to check to see if we can add those roots together, and we can't because root 5r is not the same type of term as root 8r minus 2. So what we're going to do is we're going to get 1 square root on each side of the equation, just like the last example. So to undo that, I'm going to add the square root of 8r minus 2 to both sides. So after I simplify that, the left side now is just the square root of 5r, and the right side is the square root of 8r minus 2. Now just like before, when the square roots are isolated on their own sides, we're going to use squares to undo them. So we're going to square both sides of the equation. So we get 5r is equal to 8r minus 2, because the square roots in the square undo each other. So we're just going to collect like terms here. So we get that negative 3r is equal to negative 2. And then to get r alone, finally we'll divide by negative 3, which leads us to the answer that r is equal to 2/3. Of course, we need to check our answer. We think that 2/3 is the correct value. So I'm just going to move our work out of the way here so we have a little more space to check. So the original equation, we think that the square root of 5 times 2/3 minus the square root of 8 times 2/3 minus 2 should equal 0. Now we know if two things are subtracting to be 0, they're the same thing. So here we get the square root of 10/3. Not sure what it is, but I know I don't really care at this point. And then here we get 16/3 minus 2. 8 times 2 is 16 divided by 3. I'm going to keep simplifying. I know that 2 is the same thing as 6 over 3, so we get common denominators. So we can see here that 16/3 minus 6/3 is 10/3. And of course, if I took something and subtracted itself, that would give me 0. So we know our answer is correct. Now this last one's most important. So we can see that we're involving an equation with the square root, but now there's a variable on the other side, which doesn't really matter. Again, we're going to follow our list of steps. We want to get that square root all by itself, which it is on the left side of the equation. So to undo that, we're going to square both sides. The square and the square root undo each other, so we have 2x plus 3. But now x squared is a part of our equation. And we know that this is now a quadratic equation. And when we solve a quadratic equation, the best thing to start out with is probably getting it equal to 0. So I'm going to subtract 2x and 3 from both sides. So those undo each other, so we're left with 0 is equal to x squared minus 2x minus 3. At this point, we need to find any method we want to solve this quadratic. I'm going to factor it, because I definitely realize that there are numbers that could multiply to -3, but add to -2. That'd be the numbers -3 and +1. So I'm going to use that to factor this side. I know that this would be x minus 3, and then x plus 1. So we're going to use the zero product property here. So either x minus 3 was equal to 0, or x plus 1 was equal to 0. So we get x equals 3, or x equals -1. Now in a type of question like this specifically, if you don't check your answer, you're going to get something wrong. As we can see, we're dealing with a quadratic. The other questions, it's important to check our answer to make sure we were right. What we're going to notice here is that we got 2 answers, but they're not guaranteed answers unless they actually make the original equation true. So we're going to need to actually verify our work. So to verify our work, since we have 2 different answers, we got to try them both. So let's see if x equals 3 is a solution. So if it's a solution, it makes the original equation true. So we have 2 times 3 plus 3, all under the square root. That should equal x, and we think our x value is 3. So 2 times 3 is 6, and we know 6 plus 3 is 9. So the left side of this equation is root 9, and we do know that the square root of 9 is equal to 3. So this is a solution. We'll go check the other solution here. Check x minus 1 as a solution. Or sorry, x equals -1. So we should have 2 times -1 plus 3, all under the square root, and that should equal x, which we think is -1. So as we do this math here, we see that 2 times -1 is -2, and -2 plus 3 is 1. Now with this one, the square root of 1, now this is not true. We'd expect the square root of 1 just to be 1, because we understand that we only need the plus or minus when we're actually solving something. But here, the idea is we can only use positive numbers as roots anyways, so our answer should be a positive. So what we're seeing here is that x equals -1 is not a solution. This is sometimes a little bit easier seeing that -1 is not a solution on the graph. We can see the points touch right here at the x value of 3. So we can definitely verify visually that that's a solution. Now if we look at -1, we can see that our points don't touch there. Because the square root of 1, know that the original function, the square root of x, the range of that was always positive numbers, just because of we can only take the square root of 0 or bigger. So if the smallest number I can take the square root of is 0, that means my smallest output is 0, and everything's just going to get bigger from there. So originally we knew that the range would never be negative anyway. So when we're talking about taking the square root of 1, we only are looking for positive answers. So we'd expect a positive 1 instead of a negative 1. This is called an extraneous solution. You must always check for extraneous solutions, especially when you're solving an equation that starts with a radical, but then ends up using a quadratic.